Oh, that's sweet. Hello, I'm Jim. I work at a database company. Well done, you guys. I mean, did you just look through the agenda and pick the most boring title? Is that what you guys? Is that your guys' thing? Are you like the oddballs in the conference? So you're the oddest balls in the oddball conference. Well done. Well done. Yes. Honestly, you thought graph theory? That's what I need after lunch? Oh, fuck, right, well. This is rock and roll compared to category theory. Okay, yeah, well. Good counter heckle. This is already started brilliantly. So I'm going to talk a little bit about graph theory. Not the hard stuff, because I haven't read that far in the book yet, but some of the easier stuff. So I work at a company called Neo4j, and the reason that I like graphs a lot is because Neo4j is a graph database. It's a database that lets you store and query graphs. It's pretty interesting. And I think what I've learned in the last half a dozen or so years of working with graphs and then subsequently working at a graph database company is that graphs are really cool. They're really, really cool. There's some really, really awesome properties about graphs and graph data. And I just want to kind of just share some of that with you because it's like, I can't believe more people don't know about this stuff. It's fucking amazing. It really is. Oh, I'm quite sweary, a little bit sweary. But I guess we're in Britain, not America, so fuck it. This is what we're going to talk about then. So data models, kind of historical data models and how that kind of traps our data a little bit, makes it a little bit cumbersome to work with. And then I'd like to introduce you to one possible graph model. It's the graph model that I work with mostly because it's the Neo4j graph model. It's called the labeled property graph model. And then the kind of meat of what I want to talk about is predictive and then retrospective analytics. So I've got two kind of meaty examples to work through involving using graphs to predict the future and then using graphs to very, very rapidly take account of the current context and help us to make decisions. So kind of retrospective and future-spective analytics. And then that will be it. They're synonyms, aren't they? I've just realized. Southeast London and World War I. They are synonyms. Oh, well. This is where we are then. Thank you for sending me over that schema, by the way. I told you it would be a bit of a giggle if we put it on the screen. Meh. We've been through this. That's not your schema. I know that you're at like the alternative programming conference, but at least half of you still have that schema in your workplace, right? There's some nodding of heads here. There's at least one or two of you in the room like, how the fuck did he get hold of that? We've been through this, right? We've had, like, you know, a generation now of pushing relational databases to the envelope and beyond. And now we're all, frankly, getting a bit tired of wasting our time doing the inner, left, right, outer, upside down, twiddly round, turn the ground, touch the ground, join through 17 different tables just to turn that flag from true to false. Yeah, we've reached the end of our patience there. And there are a bunch of other compelling reasons as to why the relational data model that's held sway over us for the last generation is starting to creak. Not the least of which is, you know, set union for large, unpredictably sized sets. Bad idea. Bad idea. So along we have, you know, in recent years, a bunch of new data tech has come to the fore, and I realize that there are a bunch of samurai basho types around here. So I'm going to be gentle because there's no exit apart from that one, and I reckon they've got it covered. So, so we've got things like key value stores. The key value stores are really cool. The programming model is lovely. It's a big fuck-off hash map. And I think everyone in this conference knows what a big fuck-off hash map is because it's like page 1 of the Read the Closure book. Yeah, I've learned you a good closure for great Haskell awesomeness. It's page 1. Big fuck-off hash maps are awesome. And the lovely thing about key value stores is that they are operationally really, really straightforward. I think one of the most amazing things about this category of database is that you can simply operate more and more and more of them with a stable, you know, very scalable amount of operational effort. The flip side is that they're big hash maps. So you don't get a lot of insight into your data other than by key and value. And where the keys are lying through your data, you kind of get natural indexes emerging, so you get a little bit more insight into your data with these things. And there are some very amazing bits of data technology in this category. I mean, the geek intelligentsia will argue at length whether the most scalable column store is Cassandra or HBase or that thing that you rolled yourself using in-memory grid compute daemon thing, Docker. And you're all wrong. The most scalable column store is the British Museum. This is it. It's got columns. It's where we store all the things that we stole, and when we want to scale it, we just build another wing. So it's very, very scalable column store right there. And finally, we have the document databases, as exemplified by the likes of Couchbase and MongoDB and so on. And if you ever wanted to leave information technology as a career, just Google MongoDB is web scale, watch the cartoon, and hand in your notice. The document databases, huh?
The creator is next up after you.
Really? Oh, there's twice now I've managed to miss him. Yes, give him a hug for having an even more cynical view of IT than I have. So the document databases, I think, are wonderful because as developers, they have the friendliest of metaphors. It's a filing cabinet, stick documents in, take documents out, and put indexes across them. That's it. Lovely. What's interesting about those three kinds of databases, the key values, the column stores, and the document databases, is that they share this similarity. And Fowler and Sadler's in their book, NoSQL Distilled, called this out as being aggregate-oriented. And they point out that these kind of databases work brilliantly when you have symmetric storage and retrieval patterns. That's when you want to store a customer, retrieve a customer, store a shopping basket, retrieve a shopping basket, and so on. These things are a doddle. They're a pleasure to use. But when you want to slice and dice them, when you want to know about trends of certain customer segments within certain demographics, within certain shopping baskets, within certain product types, then you tend to have to flip from a kind of query model that we used to, even with relational databases, to a kind of compute model. You kind of compute across the data to get your insight. That is, you kind of jailbreak your data out of the database, run it through your compute infrastructure, your Spark or Hadoop infrastructure, kind of grind away, and then get your answer that way. And it's a little bit odd, right? Because data likes being in the database. It's sort of swimming around in the amniotic fluid of the database. Every database, you'll find if you do source code analysis, there's always something labeled amniotic fluid in there. Class amniotic fluid or its modern equivalent. It's a true thing. It's a computer science thing. You get taught it at Oxford University. Awesome. MSc, not sponsored by Oxford University. So you have to jailbreak it. This is interesting, right? Because we're used to not jailbreaking data in relational world. In the relational world, we are very used to kind of building a high fidelity model of data and then querying it for insight rather than ripping the data out of the store and computing. And this is driven in part by complexity. It's driven in part by a sheer volume of data that we're processing. Relational stores are poor at processing large volumes of data. But I don't think complexity is merely a function of size. Size is certainly important. I mean, you can always pull up a Gartner graphic that tells you you're processing twice as much data as last month, and last month was 4 times as much as the year before, and blah, 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 blah. But it does feel that we're doing more and more with data. Certainly, we're recording more and more of our own personal movements. The granularity of data we're storing is ever finer. We are simply storing and processing more things. But the nature of the stuff that we're storing and processing is changing quite a lot. The data that we're storing and processing sometimes is really uniform, it's really regular and well-behaved and pleasant. And sometimes it's not. Sometimes it's kind of sparse and irregular and disuniform. Is that even a word? I don't know. I'm not terribly good at English, having never properly learned it. And sometimes often that data, in fact, is interconnected, intertwingled together. That's another computer term. I went to a really shit university, as you can tell. Sometimes that data, a lot of time, that data is connected. And my colleague, Alistair Jones, drew this relational crossroads thing, he calls it. And we're in a really interesting position in the data landscape today, where on the left-hand fork in the road, we have most of the NoSQL databases, most of those styles, the aggregate databases, where we have a very denormalized view of data. And in order to gain insight, we take data out of the store, process it, and compute answers. On the right-hand fork in the road, we have the graph databases in particular, where compared to relational databases, we actually have a richer, more expressive model. And instead of computing for an answer, although that's possible to compute over graphs, we tend to query a high-fidelity model to gain insight. And really, this is, if you imagine relational databases are a big speed bump right here, our choice is to fork right or fork left. I think, and this is not at all politically me, but I think we veer to the right, because we already know graphs. You already get graphs. Who's not a Londoner? Fucking hell. That was unexpected. Okay, who doesn't live in London? That's a better question. Okay. Who's visiting London for the day? Very good. Okay, you guys are now my target. So in a moment, get down to my office at London Bridge. How do I do that? Taxi. There's always one smarty pants who says taxi. Let me remind you, this is London, and I can't afford the second mortgage. So let's rule out taxi, or at least let's call that a high-cost path. How else might I do it? What are the rules in a graph? Well, you know that you can't just teleport from Paddington to London Bridge, because we know that the rules are you're only allowed to traverse relationships that are connected. So I can go from Paddington to Edgware Road. I can go from Paddington down here to Notting Hill Gate or whatever. I can go from Paddington via Edgware Road to Marylebone, blah, blah, blah. I'm only allowed to go to those dots that are connected by lines. Does that give you a better clue how I might do this? Well, you visitors, particularly if you're from America, you will say, Jim, well, it's obvious that you go down the yellow and green line, because that's its name, it's the yellow and green line. Anyone tries to give you some Englishy sounding name, they're just joking. It's called the yellow and green line, everyone knows that. So go down the yellow and green line, and then go all the way here to Monument, and then change onto the black line to go to London Bridge. That's a legal path through this graph, right? Turns out the yellow and green line is quite an expensive path because it's a bit shit. That's the locals giggling, they know the trick. It's quite slow, trains often break down. It's really confusing because although it looks like there's like one line here, logically there's like several and they are really confusing. And if you are from out of town, this will puzzle you and get you lost and probably mugged. So another way you could do this is to take the brown line, which sounds kind of rude now I say it out loud, to take the brown line to the silver line and go, make the sound effects. Do make the sound effects on the tube. People don't think you're a mentalist if you make sound effects on the tube. It's a very welcoming place, the London Tube. But feel free to make eye contact. People like that. It's a friendly, engaging environment. So I might go down the brown line, onto the silver line, then round, and then up to London Bridge here. And in fact, having empirically done this, because I used to go the other way for work every day, I actually find that the silver and brown lines are the fastest way to get across town. Notice I didn't go up, round here, down, left. Why? Because we know that's a high-cost path. So we implicitly already know how to deal with graphs at a human level because, millions and millions and millions of us deal with this graph on a daily basis. And let you into a little bit of a secret, half of those millions and millions and millions of people who use the tube on a daily basis are below average intelligence. All this given to us, although actually in this room, for the population that is this room, half of you are below average intelligence. I side with you, I tell you, I'm with you guys. All of this because of the Emperor of Prussia. So the Emperor of Prussia is going to visit Königsberg, Kaliningrad now. And he wants to see the city, but he doesn't really want to expend much energy. So the challenge is sent forth. I want to get around Königsberg, but I want to do so with minimal effort. I only want to cross each of the 7 bridges of Königsberg, spanning the River Pregel, once and only once. So you can imagine he sends out an army of flunkies who are kind of plodding around like, I've been on this bridge before, bugger. Start again. Okay. So yeah, because emperors can do this. Go, flunkies, walk. This dude, Leonhard Euler, a bit smarter than that. He's like, actually, it's kind of like, if you think about it, he's kind of like the original Lisper, because he's like, look, what I'm going to do is I'm going to build the tool, and then when I built the tool, the problem is trivial to solve. The tool that he happened to build was graph theory, and then the problem was trivial to solve. So Leonhard Euler said, no, there's got to be a way to do this without, schlepping round the 7 bridges. And what he did was, he actually did what a lot of good software engineers do, is he took a real-world problem, that kind of thing that's sort of poorly articulated to you by your product owners and product managers, and he stripped out the noise. His realization that the problem wasn't really about emperors or rivers or bridges, but it was simply about stuff being connected to other stuff. That's the important thing. That's the nub of this problem. And once he figured out the kind of logical representation, he was able to build kind of an executable representation. Obviously, not in Java, but in terms of graphs. So he actually took a real-world problem, created a kind of formal mathematical tool around it, and then executed the problem. And in fact, by doing so, he was able to demonstrate, no, it's not possible to walk the 7 bridges of Königsberg without crossing each bridge once and only once. Why? Because each bridge actually needs an even number of entrances and exits for us to be able to do that. And you can see trivially here that that does not hold in this graph. But you know, I think that's a kind of an amazing concept. It's like, you know, cut to the heart of the problem and then solve it. Fast forward 274 years, which is a lot longer than, for example, E.F. Codd's relational models being around. Just, you know, if you want to compare prowess of mathematical models, then it's only, you know, 230 odd years older. And now there are a variety of uses of graph theory in computing science, in mathematics, in anthropology, in sociology, and so on. And in the branch that I work in, we have a very simple model. We have this thing called the labeled property graph model. And in that model, we have nodes, the things where you store data, your entities. And nodes can have properties on them, so you know, actual user-level data, and they can be labeled. So they can be given a role or a tag, or otherwise taxonomized within the network. And connecting those nodes together, we have relationships, and relationships are directed, they are named, and they can also have properties. So you can do things like weighted graph walks and so on. If that seems a bit abstract, let me explain this to you through the medium of retro Doctor Who, which is the obvious medium for teaching graph theory. This is Matt Smith. Hello, Matt. We liked you. You were good. The bow tie thing? Not so. Wow. There's not a lot of like Doctor Who love going on here. That's a bit worrying. Are you Americans? No. Okay. Do you know what a Dalek is? Very good. Good. So when I teach this in the US, I am horrified to hear a phrase like, what's a Dalek? And I'm like, oh, you are so many levels wrong, dude. So this is Matt. Hello, Matt. You were good. And Matt is a Time Lord. In fact, he is from the planet Gallifrey. So here we have the simplest possible graph here. Doctor from Gallifrey. Not Gallifrey from Doctor. You can see it's directed, it's named, and so on. Great. So we know one thing about the Doctor. Of course, you know, if you only watched all of the series from 1963, Episode 1, An Unearthly Child, you'd already know this. I presume the homework assignment wasn't handed out. The Doctor stole a TARDIS. So the thing is with these Gallifreyans, these Time Lords, they've invented the ability to travel in time and space, which is frankly amazing. But they're a bit boring. So they're a bit kind of fusty, academic-y, and they just rather sit around and watch the universe turn to shit than actually get involved. The Doctor is a young, impetuous Time Lord. When we first meet him, he's about 900 years old, so he's fairly young. A bit older than Yoda, but, you know, still fairly young. And he wants to get stuck in. So he steals this vehicle that will allow him to travel in time and space, and goes barreling off around the universe, setting right things that have gone wrong. And in doing so, he makes a few enemies. He kind of makes this antisocial network. So the Doctor is an enemy of the Daleks. That's for you, obviously, just between us. He's an enemy of the Cybermen, and he's an enemy of the Sontarans. Now, the Sontarans don't appear super lots in the Doctor Who mythology, but because I nicked this slide off my mate Ian Robinson, he stuck the Sontaran in because he says I look like one, which I think is a little harsh on the Sontarans, in all fairness. But the Doctor also has this other kind of backstory going on. He likes to travel with companions. He's quite a needy guy. And until relatively recently, he was travelling with these guys. This is Rory, and this is Amy. You can see that Rory is a companion of the Doctor, and Amy is a companion of the Doctor. But these guys, so there's a bit of social network as well. These guys have their own backstory going on. In fact, they love each other. Like Rory loves Amy. Amy loves Rory. They're married. They have a child. The child is River Song. The River Song is married to the Doctor. It's like... Anyway, something graphs. Thanks for leaving me hanging there. That's just delightful. What's interesting, though, right, is that, look at this one. Loves is interesting because as nerds, as you all are, you know that it's not necessarily a symmetrical relationship. You know, so you've been in that situation where you have loved that normal person who is not a nerd, and that normal person doesn't know you exist. In that case, you wouldn't have the two loves relationship. In this case, it's nicer, loves. Anyway, so then, of course, you've got the real world of Doctor Who. And the real world is not, don't worry, I'm not a mentalist. The real world is actually where I don't know, it could go either way, right? There's a nervous guy down the front here who's thinking, oh my God, this crackpot thinks this shit's real. But there is a real world of Doctor Who, and it's the world of the script writers, of the actors, of the locations, of the costumers themselves, and so on. And all of these multiple dimensions of mythology and real world stuff get brought together in the episodes that we see that the BBC screen to us. So, if I was to ask you in which episodes did Amy battle the Daleks, even if you didn't know Doctor Who, and even if 2 minutes ago you didn't know graph theory, you could figure that out now simply by following lines, where you could say that Amy appeared in this episode, and oh, if I go up the arrow this way, the Daleks appeared in this episode. Therefore, this episode is a candidate for one where Amy battled the Daleks. Gives it away a little bit that it's called Victory of the Daleks, but you know. So, that's all you need to know about the property graph model. Compare that to that book on relational databases you read at university, which was yay thick. One slide, really. So now we know that, we can start to do some predictive analytics. And we're going to start predictive analytics with this notion of local properties. And graphs are a bit topsy-turvy, I have to say. So I'm just going to remove my Zuckerberg hoodie. It's a graph thing, you know. You have to have a blue hoodie if you're doing graphs. It's uniform. Graphs are a bit topsy-turvy, right? So in graphs, the important stuff happens in the small and the weak, not in the big and the strong. And local properties are one of these really cool, this is a local property around where I live in East Dulwich. I do like this bit, like Turkish, Greek, Mediterranean food. Nice. Off license, booze, good. But just in case you're in the mood for something really bland, there you go. They've got you covered. So, local properties. The first thing I want to talk about is this notion of triadic closure. And this is nothing to do with, you know, kind of the functional closure. It's really a very posh way of saying make triangles. But the graph theoreticians, they're a bit like the Haskellers. They want to sound wizardly, so they invent names like this. Triadic closure! I like that. That was quite good, actually. So you can see this is a little social network here that I've stolen from South Park, actually. So you've got Kyle, who's friends with Stan, and Carl, who's friends with Kenny. And as humans, you kind of see the pressure in this little graph, right? Because if Kyle likes Stan and Carl likes Kenny, it's pretty obvious at some point that they're going to introduce, and because Carl likes them, somehow there's kind of, they've been pre-selected to be potentially good friends. And you've seen that in your own work lives or in your own personal lives, right? You've got a couple of mates who've never known each other. They bump, you know, they get introduced through you, and they themselves become friends. It's quite a normal, natural reaction in graphs involving humans. So in fact, we could close this triangle, making a triadic closure, and we can have this structure here where we have three friends. I promise I won't do that again. And this is what I think of as kind of a low energy state in the graph. So you can imagine if you've got a graph like this, you could simply go around it trying to make triangles and then see how the graph mutates. Now, there's another notion to triadic closure, structurally balanced triadic closure. So it's not just close the triangle, but close the triangle based on sentiment. Now, in this triangle, I've got a few different kids from South Park. This is Cartman, who is he's actually my hero. Modulo the occasional genocide. He's like a murderous, nasty, fat 8-year-old boy with a bad voice. I don't know why. I just like him. And he's friends with Craig, but he doesn't like Tweak. In fact, there's a whole episode where Cartman mixes it up so that Craig and Tweak have this big fight. And so we could close the triangle like this. We could say that Cartman is friends of Craig, Cartman remains an enemy of Tweak, and Craig and Tweak are friends. That's kind of an uncomfortable triangle. So we've closed the triangle, we've made a closure, but something feels odd about it, right? Because like Cartman talks to Craig and he's like, hey Craig, Tweak is such a douchebag. Come on, Americana, that was for you again. Oh. As a Brit, that wasn't so, you don't watch it, wasted. But that's a bit odd. It's a bit odd, right? Because like Tweak's like, no, seriously, sorry, Craig's like, Cartman, no, look, Tweak is my friend, so don't badmouth him. So that's really awkward, right? The graph kind of rejects those kind of triangles because they don't balance, they're not stable. Instead, what you want to do is this. You want to have Cartman and Craig being friends, and then they both hate Tweak. Kids are bastards. They really are. This is not, for what it's worth, in any way like a good moral story. I'm just saying that in graph theory, from graph theory terms, it's a structurally balanced triadic closure. A better triadic closure from a kind of moral perspective is this one, 3 friends. So Carl, Stan, and Kenny are friends. That's also a low energy structure. It's a stable structure in the graph. And what's more, it's a little bit nicer, right? It's not kind of like schoolyard bullying. And it turns out structural balance is a really, really good and predictive analytic technique. And I want to demonstrate this to you by borrowing from the Easley and Kleinberg book, Networks, Crowds and Markets, which is a phenomenal book, by the way, well worth a read. This is a graph of the great houses of Europe, kind of middle of the 1800s. And you can see the kind of big players represented here, where the red relationships imply enemy, and the black relationships imply friend or ally. And obviously, weirdly, Italy is a bit neutral. And this, this structure is known by historians as the Three Emperors League, with these guys being in league with one another against the UK and France, who are, as history would always have us, bickering between ourselves. Not anymore, of course. We now share an aircraft carrier. That's how far we've come in military relations with France. It's going to make it awkward when we want to invade, though, isn't it? So let's make some triangles. We can make this triangle. We can introduce Italy into the graph. Italy becomes a friend of Austria and a friend of Germany, making a stable triadic closure here. This is known as the Triple Alliance historically. And then, actually, we can, you can see how the graph evolves again. In fact, in this case, we can now see what happens when France and Russia have a lapsed enemyship and, in fact, become allies. In this case, we've made a triangle, but it's not, it's not good for Britain, is it, here? You've got this balanced triadic closure here where France and Russia are friends, and then they both hate the UK. This is not looking good for those of us stationed here. Please, Englishmen, stop beating us up, or something like that, or the Latin equivalent. Est-ce qu'il y a des Français dans la salle? Perfect. It definitely means please stop beating us up, England. We're sick of it, and you guys are awesome, and we suck. But in graph theory terms, what does this mean? It means that we've got this really kind of ugly triangle here, because like the Brits and the French are friends, the French and the Russians are friends, but the Brits and the Russians aren't friends. That's awkward. That's the Tweak and Craig problem. So then what happens? Okay, well, the graph rejects that unbalanced triadic closure, introduces an ally relationship between UK and Russia, and then just iterating over the remainder of the graph, you find that we end up in this naturally stable state. I mean, this is amazing, right? Because now the graph is, all of the triadic closures are structurally balanced, which is brilliant, right? How did graph theory know about this? It didn't. It just closed the triangles. As you see now, on the left-hand side of the screen, you've got the allies. Sorry, Pablo. You're going to get, on this side, in your adopted mother country, the bad guys, I'll call them, for purposes of education only. So, graph theory, yeah, you predicted the starting condition for World War I, which, on a human level, that was a bit of a mincemeat machine. And in fact, this is a very, very straightforward illustration of the predictive power of graph theory. And in the Easley and Kleinberg book, they work through this, and it's phenomenal to read through this story and just see how by making structurally balanced triadic closures in the graph, you start to predict some amazing outcomes. It's really surprising. Oh. It's a bit addictive, that one. Just one more. It is that good. So there's this other thing going on in graphs, in predictive analytics in graphs, around strong triadic closure. And that's the notion not just of sentiment, but of strength in those relationships. So here you might see that we have the same kids in the elementary school again, the junior school again, and you've got Kenny, Stan, and Cartman. Kenny's a nice guy, he's friends with Stan, he's friends with Cartman, but Stan and Cartman are kind of like a little bit meh about one another. They're kind of mates, but they're not good mates. And these weak relationships, these are really important in graph theory because they identify bridges between neighborhoods. So it turns out, often is the case, and you probably notice in your own lives, you never get to hear of a new job directly from your mate. Because it turns out in your neighborhood, in your subgraph, everyone knows what everyone else knows. Gossip spreads very quickly. But you often tend to hear about a new job opportunity from a friend of friend who's not directly in your subgraph, who's a weak link to you. And so these weak links kind of play this super important role that they bridge neighborhoods. Now this is actually a graph of South Park Elementary School again. It could actually be a graph of IT, sadly, because the boys are over here and the girls are over here. And that seems, sadly, the way that we are at elementary school level. But you can see there's kind of a cluster here, and then there's this weak bridge that bridges this neighborhood, and then another kind of subgraph over here. These things, these local bridge properties, are super important because they enable you not only to see things like channels of expertise in your organization, but they enable you to start picking apart or decomposing a graph and predicting how a graph might fall apart, rather than, with triadic closures, how it might kind of build up. So in this case, here's a graph of a university karate club, an American university karate club in 1978. This is actually an example written by Zachary in the 1978, 77 American Journal of Anthropology. Yes, the long winter nights do fly by in my house, you're absolutely right. And what's interesting about this is that we know what happened again. This guy here, Node 1, is the student president of the club, and formed the club and was an instructor. He's an instructor in the club. As the club's grown, they needed another instructor to deal with the volume, so they brought on Node 34 here, which is a professional instructor. And kind of you humans with your clever vision and intuition and so on, you can kind of see there's sort of two clumps emerging here. So the question then becomes, what happens if we start to pick apart this graph? We know from the Zachary paper that there's kind of a little bit of bad blood in the club, and there is a kind of sentiment that the club needs to split. Well, what happens if we apply some of this departitioning or partitioning algorithms to our graph? Well, graph theory, if you partition it, predicts this split of the club based on the embeddedness of individuals around the student president and the professional instructor. And so you can see that the kind of pink shaded nodes here, according to graph theory, would break away into one faction, and the white shaded nodes, according to graph theory, would break away into another faction. And what's really interesting is that graph theory gets this wrong. It's kind of a bit of a bum note to end there, but thank you for your attention. No, I'm kidding. So this is really interesting. Graph theory is good at predicting, but don't bet your pensions on it, because what graph theory didn't know was this. Number 9 is clearly more embedded in the network of the professional instructor. He has more friends and colleagues and is directly connected and blah, blah, blah. But number 9, student 9, ends up staying with the student president. Why? Because what graph theory can't know is that student 9 was 2 weeks away from gaining his black belt under the tutelage of the original president. Therefore, it was not in his interest, though his graph was much more attached to the new guy, to move. So graph theory is awesome. It's brilliant for predictive analytics. You can get some really statistically good outcomes. You can mutate your data sets for what-if kind of scenarios really, really well. It's so, so powerful. I encourage you to explore it. It's amazing. The other thing we can do with graphs is look for patterns in them. And in Neo4j, we can retrospect over graphs looking for patterns. In Neo4j, we do this with a query language called Cypher. So you can tell the database, hey, find me patterns like this, where Jim has friends who like a restaurant in London and where that restaurant serves curry. And I first used this approach several years ago when I was doing a proof of concept for one of the large retailers in the UK. And we'd heard this story, and we wanted to do recommendations, and we'd heard this story that at Walmart, on Friday nights, they put the beer next to the nappies, and by doing so, sell more of both. And we thought that was a really interesting urban legend. But it was kind of one of those things where we wanted to use that as a basis for testing real-time recommendations to customers. In the UK nowadays, you swipe your loyalty card on the way through the checkout, and the checkout operator will put vouchers in your hand. Think back even kind of 10 years ago, that didn't happen. You'd swipe your loyalty card, and then 2 weeks later, some letter would come through your letterbox. You think, oh, that's spam from the supermarket, and you just chuck it in the bin. That's not a really good way of changing your buying behavior. It turns out that the psychologists know something about humans, and that is as follows, that most humans aren't psychopaths. Thank you for not being a psychopath. So what do? We built a graph of stuff. We built a graph, 2 graphs that intersected, really. We built a graph of products, product taxonomy, and we built a graph of user behavior and purchases. So the graph looks a bit like this. So we have kind of a tree up here of booze and baby stuff and consumer electronics. And then we have individual customers who have bought individual products. So you can see here that this guy, Mickey Smith, yes, a Doctor Who character, obviously, has bought Pee Wee Pilsner, Badger's Nadger's Ale, Baby Dry Nights, which is a kind of nappy, and he's bought an Xbox 360, because this was a long time ago, right? He's not bought the new Xbox. So we dumped that data in Neo4j. In fact, when I first did this, I dumped it in Neo4j when it was a loose collection of Maven-infested Java libraries. It wasn't as lovely as it is today. Now it's lovely. And we started to think about useful patterns that we could identify to change buying behavior. And since we like the Walmart example, we started to think about, well, wouldn't it be nice if we could identify young fathers? So we think we've got a young father here in Mickey Smith because he's bought beer, he's bought nappies, and bought an Xbox. And the kind of thought process there is, well, you bought nappies because you've got a baby, you bought beer because you don't go out anymore because you've got a baby, and all you want to do when little Diddums finally gets his sorry ass into bed is sit there with beer and shoot things. Because you can't shoot the baby, not allowed, you get put on a list. But you can blast zombies or aliens or, yeah. Yeah, that's the pattern. So that was a bit too much there, wasn't it? That was a bit behind the curtain there, yeah. You can, so that's the pattern we're looking for. So we thought, what's that pattern look like? So we've got someone who we know is male and has a certain birth date. This birth date becomes more and more elastic as I give this talk, actually. I'm young, will probably be like 70 by the time I finish giving this. And they bought something beer, bought something nappies, and interestingly, bought something game console. But if we want to change their behavior so that they buy a game console, maybe it's the inverse we're looking for. Of course, when we got to game consoles, and we were, in our minds, we were thinking about young fathers, booze, games, babies. It was pointed out to us that this might also be a pattern for really, really hardcore gamers. And so what we decided that we would look for, you saw it now, you can't unsee it. I know, that's really fucked you up for the rest of the day. I actually Googled that Heathrow Airport, man, the number of shoulder surfers was just disconcerting. So what we really want to do, well, actually, we're dead interested where there's a relationship between the kind of current user and they bought something in the category of nappies or baby, and they bought something in the category of beer or generally in booze, but where we can't find a link over into the game consoles, because then we can try and print them a voucher that says, hey, 20% off game console. And of course, when I first did this, the Oracle DBA said, well, yeah, obviously, what we will do is we will pre-compute everything. And then we will be able to give recommendations very quickly because yesterday we will have pre-computed all recommendations for all people. And it will only take just less than 24 hours. I'm like, well, let's hope you don't get a single more customer then, boys. And it was boys because Oracle DBAs are apparently just exclusively male and difficult. That's a valiant defense, sir, valiant defense. It's not their fault that it's Oracle. Yes, I want to believe that. Where was I? Oh, yes. And so we kind of thought about that, and the psychologist folks were like, yeah, so here's the problem. You kind of go, beep, frozen peas. I don't know why frozen peas. Beep, bacon. Beep, beer. Beep, Xbox 360. I'm quite good at checkouts. Yeah, kind of a few more items. And then, because yesterday the recommendations were computed, a voucher comes out and it says 20% off Xbox 360. But I just bought one of those. So there's this thing, it's called a contra-indicator. We thought of it as fuck you, actually, whereby you buy a bunch of items right now, in modern parlance, right in your clickstream. And then we ignore that valuable data and make a stale recommendation to you. But a recommendation which is so poor, it turns out you will go and tell 17 of your friends about it. And this is pre-Twitter, right? So now most of you can tell 18 friends of you about it. Many of you have many more Twitter followers than that because it's a game, isn't it, to collect them. At 17 people, you would have such a bad experience, you would go to 17 of your friends. I don't have 17 friends, really. Certainly not 17 friends that would care, but you will go and tell 17 of your friends about what shitty experience you had at the supermarket, and that was bad because effectively we missed out on the most important data, which was the right up to the moment purchasing history in the clickstream, so to speak, nowadays. So how are we going to query this? Well, this is a graph. I'm going to turn that same graph into ASCII art text. Same graph, right? Completely isomorphic. Yeah, it just looks rubbisher. Is that even a word? More rubbish. Someone help me with English now and again, that would be helpful. So you see here that I've got this young father who's bought something that I don't really care about, which is a member of the category of beer, that's bought something the specifics I don't care about, which is a member of the category nappies, and I've bought something which is I don't really care about, which is in the category of console. And what's interesting is if I then just flatten that out, same text, just flattened, less angles, and then add some labels, so I'll make it a bit more readable, say that D is a person, and these things are categories, and then add some more syntax, like the word match, suddenly this stuff becomes legal Neo4j cipher syntax. So there's this amazing thing about graphs, that how do you query them? Well, once you've got a graph sketched out on the whiteboard, you just need this one special purpose tool. It's called a different coloured pen. And you merely sketch the ASCII art on top of the graph structure, and the hard work of querying it emerges as a function of the structure of the graph. In this case, what am I saying? Hey, database, I'm interested in this pattern. And it's where I've got a person that bought something and don't really care what that something is. This is called an anonymous node, which is a member of some category, and that person bought something else. I don't care what it is. It's a member of some other category, and I'm interested in this other category C. I'm saying I'm going to then bind my categories to particular nodes in the graph, beer, nappies, and console, and then I'm explicitly saying where the daddy does not have a bought relationship to something that's in a member of the console category. So there's no connection between the young father and the console. And of course, I get back a Doctor Who companion. So why are graphs important then? I don't know. Ask the guys over at Facebook in North London. They'll tell you all about their graph search stuff. It turns out that graphs are really excellent at providing you context, which is really what Facebook's all about. So in fact, if you wanted to ask the question, in which sushi restaurants do my friends in New York City like some restaurant located in a place where that restaurant serves a particular cuisine, tie some of these things down into the graph, so pin down New York, pin down sushi, and pin down me, and tell me where the patterns match around that graph. And in fact, you can even simplify that. Why is this so good? Because graph query is not, the latency of graph query is not bounded by the size of the data set. The latency of your graph query is bounded by the amount of graph you choose to search. So even if you've got enormous gazillion-sized graphs, you can do these searches relatively quickly because you're making a choice at query time how much of the graph you want to search. If you want to search lots and lots and lots and lots of graph because you want to make the most accurate recommendation ever, that might cost you tens and tens and tens of millis. If you want to make a fairly kind of shallow recommendation, then perhaps you can do that even at sub-milli level. These things are super fast. On this laptop, which is brand shiny new, it's only 3 days old, I can get about 14 million relationship traversals per second through it. So you can see I explore, and this is just a laptop, you can explore quite a lot of graph very quickly. In terms of actual Facebook graph search, modern graph tech means that you can implement that kind of stuff on your application. So my colleague Max DeMasi implemented a functionally richer version of Facebook's graph search in a weekend. Glued some Ruby libraries together for natural language processing, stuck it on Neo4j, admitted that being ignorant makes you quite bold because he knew nothing about this. Bit of glue code, and hey presto, he's got a working version of Facebook graph search. Admittedly, it probably doesn't scale to the same level that Facebook's does, but it was really cool. So this stuff's really, really cool for kind of real-time processing, for egocentric queries, where you're going to drop into the graph a particular user, a particular product, and then scurry around the graph looking for insight. In a range of disciplines, it doesn't have to be retail analytics. It could be mission planning. It could be fraud detection. It could be telephone networks and data center management. It could be a range of things where you're interested in absolutely bang up to the millisecond analysis. And there's work to be done. So most of us, when we started graphs, me too, I found like, this is really hard. And a lot of that was because I had to let go and unlearn what I knew about relational databases. There is no three-step normalization process in graphs and then denormalize. There are simply fluent ways of modeling that you have to learn. There are no guide rails. But once you're over this hump, you find actually a lot of that stuff that we did for modeling, particularly in the relational world or in the denormalized database, it just goes away. And you learn to embrace densely, interestingly connected structures, and you gain insights from traversing them. To help you guys over that hump, there is a free O'Reilly book you can grab. If you go to graphdatabases.com, you can download a copy of that. I wrote that with a couple of guys I work with. It's a decent enough book. And that's all I have. Thank you for attending, and I'm happy to take some questions. Or not. Ah. Well, then, no, bugger you then. Go and have coffee. Thank you for coming. It's been a lovely session for me to be in. On time.